Hello, everyone. Thanks for joining us today. It is my pleasure to introduce our colloquium speaker, Professor Monika Schleier-Smith from Stanford University. Professor Schleier-Smith received her bachelor's degree from Harvard, followed by a PhD from MIT, working in the group of Vladan Vuletic. Her PhD work is one of the important foundational pieces in the field of quantum-enhanced metrology, where she showed experimentally how to perform better precision measurements through entanglement and use exotic quantum effects to beat seemingly fundamental limits, such as quantum projection noise. She continues pioneering work in this area, and with her group at Stanford has now branched out into exploring novel quantum states and effects more broadly, and determining how to use them for a variety of exciting applications, some of which you'll hear about today, such as quantum enhanced sensing, exploring non-local interactions, quantum information processing, studying toy models of quantum gravity, and even more. She has won a number of awards, most recently including the Robbie Prize, a MacArthur Fellowship, the Presidential Early Career Award for Scientists and Engineers, and that is just reaching back 2 years, with many more before then. We are fortunate to have her virtually with us today, and I, for one, am really looking forward to hearing what she has been up to. Monika, please take it away.
Thank you so much, Nick, for the kind introduction and the invitation to be virtually at Caltech. The title of my talk today is Choreographing Quantum Spin Dynamics with Light. To talk about some experiments we're doing in my group with cold atoms. To give some general background and motivation, I need to start with my sort of whirlwind introduction to quantum information. What do I mean by quantum spin dynamics? Information, classically, as we all know, is stored in bits. Quantum mechanically, it's stored in, well, qubits. For sort of the remainder of my talk, I won't really be saying much about qubits, but a qubit is some two-state system that equivalently, as a physicist, we often think of as a spin that could point up or down. So you'll be hearing a lot about spins in this talk. And one of the first things you learn in quantum mechanics is that, in contrast to this classical bit, whenever I measure the state of a qubit, it's not a deterministic result, but rather there's some randomness, and it's a little bit like a coin toss. So if it is equivalently, if I have a spin that is pointing up, that's a well-defined state, and if it's pointing down, that's a well-defined state, but generically it might be anywhere in between, and there's this probabilistic aspect then to what state I will measure it to be in. So this is kind of one of the aspects of quantum mechanics that is a little bit funny. But what's really weird about quantum mechanics is the nature of this randomness. So it's not just any coin toss. In a quantum mechanical coin toss, you can have this weird situation where maybe Alice is in my lab at Stanford tossing coins, Bob is in a lab at Caltech tossing coins. To each of them, the outcome of their coin toss looks flat random, but when they compare notes, they will find that every time Alice got heads, Bob got tails, and vice versa, right? So this would never actually happen with a classical coin toss, but in quantum mechanics, this is allowed, these correlations within the randomness. And why do we find this so weird and bizarre, right? This is the phenomenon of entanglement, famously called also spooky action at a distance. What's so spooky about this? Well, the weird thing about this, right, is that this tells us the fact that there are these correlations between measurements performed in distant places. It tells us that actually information in quantum mechanics doesn't have to live in one place. So there's some information here that Alice doesn't have and Bob doesn't have, but when they compare notes, all of a sudden there's information there. So kind of one of the really groundbreaking aspects of quantum mechanics, right, is that information is something that can be non-local. And we find that weird because the way that we interact with the world around us is local. So in fact, quite generally, the fact that all interactions in nature are local, things interact with things that are near them, forces decay with distance, tends to restrict actually the types of quantum states that we find in nature, the sort of phases of matter that appear in materials, and even that one can synthesize in the lab. So here's a picture, for example, of some spins, internal spin states of cold atoms that have organized themselves into some checkerboard fashion, heads, tails, heads, tails. And those are sort of local correlations that arise from the influence of direct interactions between things that are near each other. So the focus of actually my talk today is going to be on expanding the range of interactions that we can realize in the lab, with an eye towards ultimately opening new directions in what forms of quantum entanglement we can realize, and I'll say a little bit about what one can hope to do with that. So just to kind of convey kind of a vision that we can strive for, right? Ultimately, the dream would be that we have something in the lab that's sort of like an arbitrary waveform generator for quantum engineers, where I can say, today I would like to have the following structure of my interactions that need not necessarily be confined by laws like locality, and program it in and maybe watch what happens or realize some particular quantum state that I know will have some useful application. So that's kind of the vision, is to start having programmable systems. And that might sound a little bit far-fetched, but actually in systems of cold atoms, there's been an astounding amount of progress in recent years towards building really highly programmable systems of, for example, individual atoms in optical tweezers. So here are some pictures from labs around the world. This includes also work by Manuel Endres, where it's possible to use use arrays of individual optical traps to fine-tune the positions of atoms and organize them into one-dimensional or two-dimensional or even three-dimensional structures. And I think I like these pictures because it's kind of a nice illustration of the exquisite level of control that is possible by taking advantage of the high degree of control we have over laser light. So the focus of my talk will be somewhat complementary to this. The focus of my talk will be on asking, how do we control not the positions, but actually the interactions between atoms? And specifically, what will be our focus, what will be sort of a key requirement in order to start to realize interesting quantum systems, is to be able to have interactions whose range is long compared to the characteristic spacing that one might have between atoms. And what's actually also often important is the characteristic length scale set by the wavelength of light, which sort of determines the scale on which we can manipulate and detect the atoms. So in these pictures I've shown you here, these arrays have kind of spacings between atoms on the few micron scale. And so correspondingly, being able to have interactions that extend to the few micron scale or beyond opens up new directions in terms of what one can do with these systems. And in particular, having some form of interaction on that scale is essential for making this not just a nice picture, but a system where there's interesting quantum mechanics going on. So what do I mean by that? So what are some of the directions one would like to be able to take these systems? One kind of direction is what we might call quantum control. Can we make specific quantum states with correlations that might have some useful applications, be it in sensing, computation, communications? Another direction is simulation. So can we program some model system that we believe might capture the essential physics of a phenomenon in a field ranging from maybe condensed matter all the way to perhaps even quantum gravity. And a third direction that you might be interested in is actually building quantum systems that can be used to solve classical problems. So, for example, a wide range of sort of optimization problems that one encounters in the real world can be mapped to the problem of, for example, finding the lowest energy state of some interacting spin system. And so if you can perhaps build that system in the lab, it might give you a way to solve these optimization problems. I'm going to start with just sort of an example from this kind of sphere of application, because it's the one you might be most likely to read about in the news. So, if you kind of read the news about why one wants to build controllable quantum systems and some of the companies that are aiming to have an impact in quantum computation, they'll tell you that they're aiming to solve things like scheduling and logistics problems. My favorite example is this one, which says they are aiming to optimize fleet operations for holiday deliveries. And I always sort of read these things and wondered, like, how do you do that? How do you actually program such an optimization problem into your quantum system? And in fact, there are lots of questions ranging from sort of, how does one map real world problems to quantum systems, to also, can quantum systems help? What role does entanglement play? But to start to explore these systems, you might want to be able to sort of build some systems in the lab that could encode some real world optimization problems. So here's a problem that I was really happy when I learned about it, because I can relate to it in my daily life. So the problem is, imagine that I have a set of n objects with some weight that I'll call xi. You can ask the question, so those objects might be my groceries that I bought, and I want to divide them into two groups that I can carry in my two arms. So the question is, does there exist a partition of these objects into two equally weighted groups? So as a physicist, of course, naturally, the way that I will try to frame this problem is to say I'm going to define the imbalance as some kind of something in terms of a spin system. We always like spins. So I'll say, if my spin is pointing one way, that would be putting an object in this one bag. If it's pointing the other way, that's putting in the other bag. And so I can map this problem into one of minimizing some weighted sum of spins that can point either along plus or minus z. It might be minimizing that sum that I call f here, or maybe it's minimizing this quantity squared. That might be more convenient. And actually, if I look at this example, this problem ends up mapping to something where what you would like to minimize is something that looks like the energy of an interacting spin system, right? So each term in this sum will depend on whether a given pair of spins is aligned or anti-aligned. So this kind of, and in particular, if you'd like to encode a specific problem, right, then you'd like to be able to have some control over the strength of interaction between different pairs of spins. And in this example, actually, you'd like any spin to be able to talk to any other. So you'd like to have really quite versatile control in the sense that these interactions shouldn't just be constrained by physical locality. So in particular, right, so the tools you'd like to start exploring this type of problem would be some quantum system in which you can encode a spin, long-range interactions, and the ability to program those interactions. Okay, so there are two different physical systems we work with in my lab that have those tools in various different forms. So in one of our systems, the way of generating interactions is to excite ground state atoms to highly polarizable Rydberg states. And that is something that there's beautiful work going on at Caltech that may be familiar to some of you. And this is something that gives rise to interactions on sort of the scale of the few micron scale, which are long range, but still have some aspect of locality to them. And then later on in my talk, I'll talk about a different physical system where atoms can talk to each other in a way that is mediated by photons. And these interactions are, in some sense, even more exotic. They can be highly non-local and can give different forms of connectivity on sort of millimeter length scales. So that's kind of where we're going. And we'll start with this sort of slightly less exotic system on the left here. Just to give a little flavor of how can one generate interactions by exciting atoms? Well, here's a picture just roughly to scale of a ground state cesium atom that's shown here as this blue point. And a cesium atom with its electron excited to a state of principal quantum number n equals 43. It's much bigger. The radius scales quadratically as I excite the electron to this high-lying state. And as a result, these atoms can become highly polarizable. And in particular, the van der Waals interaction between two of these atoms scales as this principal quantum number to the 11th power. So it's an extremely strong effect that takes atoms that would normally be non-interacting and allows them to interact. And there's a bunch of different experiments going on exploiting these forms of interactions in different ways. There's been beautiful work at Caltech demonstrating kind of record entanglement fidelity for neutral atoms. There's been applications towards studying sort of condensed matter-inspired topological physics in arrays of these atoms. And different ones of these experiments actually sort of utilize these Rydberg states in different ways. So in some cases, one might encode a spin on a transition from a ground state to a highly excited Rydberg state, or on a transition between two Rydberg states. There's a third approach that has been our focus to date in the lab, which is actually encoding the spin in two long-lived stable ground states, but using light that is off-resonantly coupling the state to the Rydberg state. So we're not directly doing physics with Rydberg atoms, but we're what we would call dressing the atoms, adding in a little bit of that character with a laser field. And this has a couple of nice features, including the fact that in some sense, the laser directly then governs the structure of the interactions. And when the light is off, one has kind of a closed non-interacting system. So the kind of experimental setup where we implement this is shown here. So far, the work I'll tell you today is done simply in the setting of a gas of atoms, a cloud of atoms. And we work with, for the experts, with cesium atoms. And essentially, again, our spin is encoded into ground states, but by turning on some light that couples one of those states to the Rydberg state, we can induce a situation where that laser field for two atoms that are very far apart would slightly perturb their energy levels. And as the atoms come closer and closer together, that perturbation changes because these Rydberg states are so strongly shifted by the atom-atom interactions. And as a result, even for the ground state atoms, there's sort of an energy shift due to the light that changes when two of these come close together. So that's the general concept. And what one expects to happen is that this energy shift is a state-dependent shift. Only one of my two spin states is affected by the light. And in particular, it takes the form of an Ising interaction, one where the z component of the energy of one spin depends on the z component of one spin acts sort of like an effective magnetic field for any surrounding spins. So one way to sort of think about, have we correctly realized this interaction is to say that if it should act like an effective magnetic field, that means that any given spin should sort of precess in a way that depends on the neighboring spins. So here's a picture where we're looking at the average magnetization in some region of this cloud of atoms. And actually, so these points are different sort of initial spin polarized states in which we've initialized the system. And we ask sort of what happens when we turn on the light. And what we see is some kind of precession rate that depends on the tilt of this magnetization. And that makes sense because it's basically saying that for any given spin, the number of surrounding up or down spins determines some effective field in which it precesses. So this is a signature of these Ising interactions that are induced by the light. Now, actually, I want to mention one reason why this is an interesting type of an interaction. And that's, so far, the focus here is just on looking what happens to kind of the average magnetization in some region of the cloud. But if you were to ask and look more closely at what happens to the quantum fluctuations, because it's a quantum system, right? When I measure the states of the system, I should get some of this coin toss noise. There should be some fuzziness in where the spin points. And these dynamics, this sort of twisting dynamic that you saw at the mean field level should give rise to some twisting of this quantum noise that actually reduces the fluctuations in a particular direction. So this is a phenomenon called squeezing. It's something that would be a signature of having quantum correlations in the system of a form that is useful for enhancing any precision measurement that relies on measuring a precessing spin. That could be a magnetometer, an electrometer, and so forth. So why is it interesting to do this in this particular way? So it's worth pointing out, actually, there's a wide range of experiments that have been done over the past decade or so, realizing some sort of modification, reduction in quantum noise through entanglement for sensing applications, ultimately, in a wide range of different physical systems, either relying on direct collisional interactions to generate entanglement, relying on interactions mediated by photons, similar to things I'll talk about later. And very recently, there have been some beautiful experiments starting to enter this regime of entanglement-enhanced metrology with small numbers of Rydberg atoms. And so there's sort of a huge parameter space here that's being explored, and it's an exciting time. And you might ask sort of, with all these different systems, how should you choose, and what are sort of the open questions to explore? And so I should just emphasize what am I showing here in this parameter space. So the red line is kind of the most precise measurement that one can do with a given number of particles if one fully exploits the quantum resource of entanglement. The black line is the most precise measurement that one can do without entanglement, and these are examples of things that are exploring the space in between. So, obviously one direction of research is sort of, can you go up in this plot, or actually it turns out up and to the right is the direction of improved absolute precision in measurements. But there are actually also axes that are sort of orthogonal to this plot. One that I won't say much about is actually taking sort of proof of principle demonstrations and really applying them to enhance things like the best clocks that are made of atoms, gravimeters, magnetometers, or maybe, actually I put this on for Nick, maybe precision tests of fundamental physics, right? But there are also sort of lots of other axes, like how robust are these states to decoherence? Are there trade-offs between the precision of a state you make and the dynamic range of the state? Can you use it for spatially resolved sensing? And so one of the sort of directions that has really yet to be explored is, can one benefit from having not just one single kind of quantum state that I can represent by this kind of picture on a sphere, but having some spatial structure to the quantum correlations? And this is a direction that benefits from having optical control of the interactions. And so just as a kind of nice illustration that's something that one has in this system, right? Here's sort of, these plots are again showing sort of signatures of these twisting dynamics indicating the interaction strength. But here I've sort of reduced that type of a measurement to a color plot. Vertical is sort of the initial tilt of some vector. Color is the phase of its precession. The fact that the phase goes one way at the top and the other way at the bottom, right? That's just another representation of this twist. And the fact that this color is most saturated in the middle says the twist is sort of strongest at some position here in the atomic cloud. So this is just showing, yes, the interaction strength is governed in a sensible way by the intensity of our laser, which is, in this case, just some Gaussian beam. Okay. So this spatial control of interactions then is actually a really nice feature of this system where one has a laser field that turns the interaction on. The locality of the interactions is potentially a plus if you want to be able to have some spatially patterned individual array of, let's say, individual entangled states. It's also potentially a challenge if you want to generate long-range correlations, right? And so it turns out that actually in these systems, a second ingredient that one would like to have a higher level of control, is to have not just this interaction, this Ising type interaction, but it turns out if I have one other ingredient, which is a transverse field, then that can give you much more versatile control over the system. And so while we were at it, we were curious, can we actually realize a so-called transverse field Ising model, where one has a given spin precesses in a way that depends on its neighbors, but at the same time, the effect of that precession can be turned into a tilt that will travel down the line and affect other spins. So in this particular example, it turns out the easiest way for us to do this is, in our system, the microwave coupling between these two states acts just like a transverse field. It can induce a spin rotation. And it turns out to be convenient to alternate in a pulsed fashion between the interactions in the field. And so if we do that quickly enough, then it's effectively like we've built this system where I just sum up these two terms. And one of the things that you expect to observe in this system is actually a phase transition between a state where the spins want to align along the field and one where they want to align with each other. So this is kind of one way of checking, have you correctly realized this model? Okay, so here's some evidence that we in fact realized that model. This is the plot you saw before, where I've shown you kind of, again, vertical represents different tilts of some initial magnetization, color represents phase, and the key thing to note is that the white color indicates that the phase hasn't changed after some time evolution. So on this particular plot, when we add in this transverse field, you'll see the white contour, sort of, which is where the state remains fixed over time. In the wings of the cloud, where we have no interactions and only this field, there's sort of a single fixed point, which splits into two new fixed points once you get to some critical interaction strength. And we can actually interpret these fixed points of the dynamics as telling us actually sort of what the ground states of the system are. And this is a signature of having sort of this one single ground state with spins aligned along the field in the wings that splits into a ferromagnetic phase where the spins want to align with each other, but it could be aligned up or down in this central region where the interactions are strong. So I think this is a nice illustration of kind of local control of interactions, taking advantage of light, where one has, in this particular case, a sort of unusual system where part of it is in one phase and part of it is in another. But that's just the starting point for applying this combination of Ising interactions and the transverse field and the ability to control these properties dynamically in a number of different directions. So I said before, these sort of Ising spin interactions feature in optimization problems. And those two ingredients are actually part of an algorithm for exploring, can one use quantum systems to better solve these optimization problems. These ingredients of optically controlled interactions are also great for studying non-equilibrium dynamics, so there are interesting directions in studying uniquely non-equilibrium phases of matter, and I mentioned before in building resources for quantum sensing. Some of these, the more computational ones, should be done not with this cloud of atoms, but with individually addressed atoms, and so that's a direction that this will soon go. So with that, I think maybe I'll just pause and ask whether there are questions so far, because if not, I'm about to shift gears to talk about a slightly different physical system.
And if people have questions, you can either raise your hand or type them into the Q&A. Yeah, so let's keep going.
Great. If not, then I will shift gears a little bit and tell you about a different physical system that gets even deeper into this regime of trying to sort of break our intuitions that interactions should be local and get to a regime where we can have interactions that can be sort of occurring on the millimeter scale thanks to having photons conveying information from one atom to another. And so this is a physical system that is, already has a fairly strong track record in areas ranging from quantum sensing, one that I touched on before, to quantum simulation, studying phenomena ranging such as supersolidity. There are ideas for studying spin glass physics, and we'll get to some ideas for exploring quantum gravity. What are the things that we're kind of adding to this toolbox? Well, a key sort of focus of our experiments is taking advantage of the ability to not only have atoms strongly coupled to photons, but also the ability to locally address and image and manipulate the system. So I apologize. Some slide was out of order, which threw me for a loop. Okay, so I apologize there. Okay, so this is a system that, again, so it has a strong track record even in the area of quantum simulation. But one of the sort of exciting directions we've been exploring in our lab is, can we extend control over the system to the point where we can start to explore actually some new directions? And so just to kind of illustrate some new features you might like to have, I'll give one example from the area of quantum simulation. Okay, and so this is a problem that has a strong tradition at Caltech, which is asking how can one understand at a quantum mechanical level what happens to information that falls into a black hole. And it was pointed out by Patrick Hayden and John Preskill that the right way to understand this, what was thought of as a paradox of information loss in black holes, is to realize that no information isn't lost, but what happens, what I should think of happening inside a black hole is that information very rapidly becomes kind of hidden in correlations between between strongly interacting quantum particles. And so the concept is that imagine I had some quantum system where I initially had some information locally encoded in this qubit. if that quantum system behaves in a way where that information becomes exponentially quickly delocalized over all degrees of freedom, that type of exponentially fast spreading could account for the phenomenon of essentially what might look like information loss. Okay, so this is kind of a neat feature, not only because maybe it tells you something if you can study it in the lab about gravity, but also because this exponentially fast scrambling is believed to be a fundamental speed limit in the dynamics of any quantum system. And so, hearing that raised for me the question of, is this a process that one could build systems in the lab that behave in this fashion? And the roadblock you immediately run into is that most systems we build in the lab, again, have these local interactions where information kind of spreads from one particle to another, perhaps in a linear fashion in time, perhaps a little bit faster if I have some long-range tail of the interaction. But generically, it's not at all obvious how you would build a system where information spreads exponentially quickly from one to many. So can you do this? Do you need to, can you structure the interactions in such a way? Well, it turns out there are models that people can write down on paper that do behave in that way. And so one of them is shown here, the Sachdevier-Kitaev model. Right, and this involves interactions between fermions that are entirely non-local. So there's some sort of random non-local interactions between the fermions in this model. And that is understood to behave in this sense like a black hole. But to me as an experimentalist, this looks hard to do. And so a question you can ask is, are there other models that might not be exactly this, but are similar in flavor? And I should mention there are proposals for realizing this model in some solid state systems. The most similar thing in flavor that sort of we naturally have access to in atomic systems is something where it's not massive particles that hop over long distances, but what the things that hop are spin excitations. So it's not exactly the same, but maybe one can access some of the same physics. And so the idea is if I can make a spin exchange interaction, I can think of that as a spin exchange, a spin excitation that hops between two atoms. And if I can arrange that sort of flip-flop process to happen in a way that is mediated by light, then I can actually make this process be very long-ranged. Okay, so what do I mean by that? So imagine I have a situation where an atom that's in the spin-up state can emit a photon, which gets absorbed by another atom, and both of them flip their spins in the process. Then if that photon, that interaction can be as long-ranged as, the photon can travel. Now, the one thing I need to be careful about is I want to be sure that that photon really hits another atom and doesn't fly off in some other direction, and so we put the two atoms between mirrors to form an optical resonator that gives us an enhanced probability that that photon will be reabsorbed by another atom. Okay. And this general idea of kind of photon-mediated interactions appears actually in a range of different settings and physical systems, ranging from microwave photons coupled to superconducting qubits to, in our case, optical photons coupled to atoms. And this has a strong tradition also here in Caltech in the form of recent experiments, for example, studying waveguide QED. So there's sort of a host of different applications you might use such systems for, and depending on your application, you might choose a different platform. I think one thing that's kind of worth pointing out, though, about the atomic platforms is kind of, they have a neat feature in terms of both, in terms of their scalability. And so there are experiments in these systems working with two atoms, implementing a quantum gate between two atoms, all the way up to studying collective dynamics and collective entanglement between hundreds of thousands of atoms. Okay, so in our particular case, the first experiments I'll show are working in some cloud of about 100,000 atoms that are trapped in a standing wave of light between two mirrors. And that standing wave basically means that the atoms' positions are confined along this long direction. And so the dynamics we will be thinking about will be occurring just in the spin degree of freedom. Okay, so here are some of the students who work on this experiment, and when they want to make their atoms interact after they have built up all these optics, it comes down to basically turning on a laser field that, well, drives a process. So in practice, we want this to be controlled by light. So we will drive a two-photon process where an atom can absorb a control field photon, flip its spin, emit that photon into the cavity, and then another atom can flip its spin by absorbing that photon. Okay, so this is something that should give rise to this kind of flip-flop behavior. And we can see that that works by sort of taking some pictures as a function of time of the number of excitations as a function of position in our cloud. So here's an experiment where we intentionally started with some excitations here, and as a function of time, we watch where they go, they oscillate over, they come back. This oscillation means there's some coherence in the system, which is good. And then another kind of striking feature, I think, is that they don't just sort of, you don't see the excitations just moving away from point A. They kind of suddenly show up at this point B and come back, and that kind of highlights the non-local aspect of this interaction. And if you want to know why it is that they suddenly show up here, that's actually something one can calculate if you just know the strength of the local intensity of the light field and the atomic density in a given region. So definitely non-local interactions. So far, it's not exactly a function generator, right? So I would love to have a system where we can turn this into something where we can control things like what is the spatial structure of the interactions. Actually, and so, you know, some spatial structures you might be interested in are every atom talks to every other. That showed up in that partitioning problem I talked about earlier. Maybe one talks to every other, which actually is also relevant in that context. Maybe you want the atoms, their interactions to be such as if the atoms were leaves on a tree. This actually has some connections to this question of can one build toy models for quantum gravity. And so if you're interested in knowing more about things that might happen with these different interaction graphs, here are a few different theoretical papers on ideas we've been thinking about. But quite generally, control of the spatial structure is one aim in this system. But there are other things you might want to control, like what is the form of the couplings? Is it just this spin exchange that I can think of as these excitations hopping? Or is it an Ising interaction, like the one that showed up in those optimization problems at the beginning? And what is the sign of the interaction? Is it ferromagnetic or anti-ferromagnetic? So let me actually start by showing you, I'd like to convince you that we have actually a remarkable degree of control over all of these things. I'm going to start with the form and the sign of the interaction. So it turns out actually, simply by controlling in our system the orientation of a magnetic field, we can tune, do we have an Ising interaction? That's what's shown here. Or the spin exchange interaction, which I can equivalently write in terms of some the x and y components of the spins. I've used some simplified notation here, where I've actually accounted for the fact that the simplest form of interaction we get in this cavity is something where the strength of interaction between any pair of spins is simply governed by the local intensity of the cavity mode. And correspondingly, in this system, I actually can write the Hamiltonian down in terms of some weighted sum of the individual spins that I had defined earlier in the talk. So that's kind of the form of interaction you would get in this in the simplest case in this system. But we can actually, in a very convenient way, tune, do we have a pure Ising interaction, a pure spin exchange interaction, or anything in between, just by tilting the orientation of the magnetic field. And just by changing a frequency of a laser field, we can control is the interaction ferromagnetic or anti-ferromagnetic. So I say that we can do that. The way that we actually test this is by doing experiments where we initialize some spin texture in our cloud of atoms, turn on the light, and watch how that texture evolves. And so for example, we can initialize a system with some spins here pointing down, and some pointing along x, and some pointing along minus x. And if there is an Ising type interaction, those spins in the xy plane will precess, and the rate and direction of that precession allows us to extract the coupling strength and shows us that we have this degree of control. Now, the rate tells us the strength, the direction tells us the sign, and one thing you might ask when I say, well, I can see the sign of the interaction by which way these spins turn is, that's not really the intuition you have when I tell you I can control is the interaction ferromagnetic or anti-ferromagnetic. The intuition you probably have is that the sign of the interaction is something about do the spins want to align or to anti-align. And so we were actually interested, can we actually prepare low energy states of this system that show that behavior of the tendency of the spins to align or anti-align. That's also useful if you want to start moving in a direction where, ultimately you're looking maybe at, let's say, individual spins and asking, can I learn something about, find the ground state of some system that solves some problem. So can we prepare low energy states of this system? The way that we do this is we start in the sort of a low energy state of a simple Hamiltonian, like magnetic field, pointing along a particular direction, and then we slowly turn on interactions and watch how the system evolves. Actually, the first simple thing we can do is not even turn on interactions. This is just to orient you. Start with a magnetic field pointing along the z direction, slowly sweep it to the x direction, or vary the final tilt and ask what happens to the magnetization. And as you might expect, the magnetization, this is showing here the z component, kind of follows the tilt of the field. So the tilt of the field is shown in vertical. But if we turn on interactions, and in this case I'm showing you Ising interactions, then you can actually see that this sort of smooth behavior turns into a knife edge where all of a sudden the spins go from all wanting to align down to all wanting to align up in the case of ferromagnetic interactions. So that makes sense. That looks like this is behaving like a ferromagnetic system. I can kind of summarize that in a plot of the magnetic susceptibility. So this is kind of how sensitive is the spin polarization to small tilts, and that starts to diverge as one approaches some critical strength of the Ising interactions for the ferromagnetic sign. Interestingly, you actually see the same behavior here if I have spin exchange interactions or XY interactions of the opposite sign. And this kind of mirror image plot, depending on which form of interaction I have, it might not be immediately obvious why that happens. But it turns out we can understand this. In the simple case, if I had really like every atom talking with an equal strength to the cavity, then this collective spin I've drawn here would just be an equal sum of the spins of the individual atoms. And in that case, I could write down an exact relationship between the z component squared and the x and y component squared, where the only difference between fz squared and minus fx squared minus fy squared is some constant term that depends on the total length of this sum of spins of the individual atoms. So there's a minus sign here, right? And that means that these plots should be flipped from each other, and that makes sense. Okay, now one thing that I didn't like about this is that if one wants to study some, let's say, quantum many-body physics in this system, you might like to have something that you can't describe as just a single collective object, right? So I was curious, are there situations where this symmetry breaks down and there's actually some difference that is some indication of having actually, a many-body system and not something that's behaving like one big spin. It turns out even without trying, there's a small magnetic field gradient in our system that starts to sort of break the symmetry between these different spins depending on their spatial location. So in our system, if we have no interactions on and just watch as a function of time what is the phase of the spins, which is shown here in color, you see some kind of a phase winding at later times that's kind of some spiral texture evolving in the cloud. Now, it turns out if we turn on spin exchange interactions, that's this plot here, then all of a sudden the phase evolution versus time looks much more boring. And this is a uniform color because the spins are just staying aligned. And so if I plot this phase winding versus time, with no interactions, it's winding over time. With these spin exchange interactions on, it's completely flat. And so we've totally suppressed this sort of dephasing due to the magnetic field. And this is something that's unique to the spin exchange interactions and doesn't happen if I had the equivalent Ising interactions of the opposite sign. So first of all, this is a nice indication that one can get beyond just these single mode dynamics in this system. And it's also potentially useful. So here it's just saying like what is the global spin coherence as a function of interaction strength in the XY case above some critical interaction strength. Essentially, the coherence of the system is actually protected. So this was actually pointed out in some experiments at Gilla that showed some spectroscopic evidence of there being sort of an energy gap, an energy difference that depends on the length of the total spin, which I can think of as responsible for this protection. In other words, these XY interactions are like Ising interactions, but with a term that says different lengths of the total spin give rise to different energies, and so I'll get stuck at a particular length of the spin. So this was observed spectroscopically, but here we can really directly observe the effect on the spin coherence. And that potentially actually has applications in situations where you want to turn on interactions, perhaps in order to generate some entangled state, but you want to avoid any decoherence effects even from that light. If you have a choice, maybe this is the type of interaction you want to use. Okay, so with that though, actually most of what I showed you so far, I can actually understand in a relatively classical sort of a picture of like spins processing around each other. And I want to kind of get to something that gives you a little bit more of a sense that this really is a quantum system. And to do that, it's actually useful to consider a situation where the spins that we're working with are spin 1. This was actually true before, but it didn't matter before. So it turns out we have actually 3 internal states that I'll call -1, 0, and 1. And you can ask the question, what happens if I initialize all the atoms in the 0 state? So now the average magnetization of the system is 0. So if my picture is something about spins rotating around each other, you would think maybe nothing will happen. But we can ask, does anything happen if we turn on, for example, this spin exchange interaction? So here's an experiment where we did that. Actually, this is a sequence of 100 repetitions of the same experiment. And what you'll see is when we measure after some time the populations in these 3 different states, you'll see large fluctuations. But whenever we see atoms in this -1 state, we also see atoms in this +1 state. So we see large fluctuations, but the fluctuations are correlated. And this is something that was a little bit familiar to me from some other contexts, where, for example, in dense Bose-Einstein condensates, one can have collisional interactions between 2 atoms in the 0 state that give you a +1 and a -1 atom. It's also a little bit like driving a nonlinear crystal and generating correlated photon pairs. But in this case, one thing that's neat about this system is these aren't direct collisional interactions. These are highly non-local interactions happening over sort of a millimeter length scale, mediated by photons. The fact that they're light mediated actually makes them very fast, which is potentially interesting and could have applications to kind of rapid generation of entanglement. But also the fact that they're controlled by light raises the question, can one start to engineer the spatial structure of these long-range interactions by using some form of optical control? So to start exploring the spatial structure of the interactions, we said, let's make our system a little bit more well-controlled and work with an array of small atomic ensembles. The fact that we have ensembles helps us actually enhance the atom-light interaction strength. And the fact that it's an array allows us to ask questions like, can I realize a spin model that I could write as like, I create a +1 on one side and a -1 on another, and control actually the spatial structure of that form of interaction. At what interaction distance is this spin exchange allowed to happen? Okay, so the dream would be to have something like maybe arbitrary control of these interactions. And actually, there's a beautiful proposal from Jeff Kimball and collaborators on how one could actually approach this dream, thinking mostly about nanophotonic waveguides, but actually this is equally applicable also to cavity QED, to sort of a macroscopic cavity like ours. So the basic idea is if I'd like to start controlling these interactions, let me modestly say I'd like to be able to realize any distance dependence of the interaction. Okay, so how might I do that? The first thing I need to do is turn off the long-range interaction. And to do that, we actually apply a magnetic field gradient to the system, so that this process of making +1, -1 pairs can only happen if the atoms involved are sitting on the same site. Because at long range, there's an energy cost to doing to making a +1, -1 pair. So here's a plot showing spatial correlations between the +1 and the -1 atoms, and those correlations are appearing only on the diagonal, which says we've made the interactions local by turning on this magnetic field gradient. If we now, though, add 2 laser frequencies, so instead of having 1 laser driving our cavity, we have 2 different frequency components, then we can bridge that energy cost of creating correlations at a particular distance, interactions and correlations at a particular distance. And so now this frequency difference ought to set the distance at which correlations appear, and in fact, that's what we see. So now we have correlations appearing at some particular frequency difference set by the spectrum of my laser field, And as I tune the frequency spacing, so this horizontal axis is distance, color plot indicates correlations. As I tune the frequency spacing of these two laser fields, you'll see that the correlations track. And this is actually, I was actually amazed by sort of how fine this control is. You know, my students can really dial in, do I have interactions at a distance of 9 sites, 10 sites, or 11 sites by tweaking the spectrum of the laser field. In principle, this generalizes, right? If I have multiple drive frequencies, I can have arbitrary couplings versus distance. One of the contexts where, you know, that we're dreaming of applying this in is building models where you can very efficiently scramble information. For example, if you had couplings at distances, even just a few distances that are, let's say, all powers of 2, then in a number of kind of hops that's logarithmic in the size of the system, you could get from one point to any other. And that type of a model is something that looks conducive, based on some theoretical work, to fast scrambling. And in particular, if you could sort of watch how the correlations spread in time, you could imagine taking this class of model and saying, well, if interactions shrink with distance, then it should look just like, you know, basically like a linear spin chain, and you should see some kind of a light cone governing the spreading of correlations. But if you start to have, for example, interactions at these select distances that are not shrinking with distance, then actually the time to reach a given strength of correlation could scale at most logarithmically in the system size, because the longest distance in the graph of couplings is logarithmic in the system size. So that's the type of thing you'd like to be able to explore. One thing that we immediately asked ourselves is, you know, can we start even in simpler models, not yet this fancy one, to ask something about how correlations spread versus time? And actually in our initial experiments, we very rapidly saw some correlations that are longer range, so correlations at multiples of the length scale on which we've turned on interactions. And we want to understand, you know, actually, is this something where they're spreading over time, or are they just appearing all at once? Because after all, it is a single cavity mode. Maybe any atom can talk to each. Maybe we haven't really broken down this non-locality of the interactions. But in fact, you know, you can, if you do a slightly different measurement, you can start to actually watch the time evolution of the correlations. This takes, this is kind of very recent and preliminary data, where we're starting to actually ask, how do these correlations develop as a function of time? Let's say in this case where I have interactions as a function of distance, and those interactions are turned on at a distance of every 4 sites, let's say. So I think it's worth pointing out that when one has this level of control, the physical geometry of your system as a 1D chain doesn't necessarily still reflect actually kind of the effective geometry given the graph of interactions you've made. So if I do this thing with interactions every 4 sites, maybe the better way to think about this is that actually I don't have sort of one chain with these interactions every 4 sites. Maybe I should really break this down and say, actually, this is a set of 1D chains that are decoupled, or if I start to couple them, it could start to look like a 2D system. And in fact, in some cases, you find if you look at these correlation plots and you rearrange them, they kind of look more natural when you rearrange the system in a different way. And this is kind of hinting at the fact that now you can start to play with effective geometries that are beyond the physical geometries you can realize in the lab. Okay, so very recently we're starting to explore, can you make something that's maybe a Mobius strip geometry? Can you build on this model I showed before and start to realize something like these tree-like geometries that could look like kind of a discretized version of curved space with some connections to toy models for quantum gravity. So with that, I just want to actually summarize and say that I've shown you 2 different physical systems where we have various ways of optically controlling interactions between cold atoms. And we have programmability of a number of different aspects: the form of the interaction, the sign of the interaction, the graph of the couplings. I've shown you one kind of useful application of controlling the form of the interaction to protect spin coherence. And particularly with these advances in spatial control, we're excited to start asking, can you generate and utilize spatially structured entanglement as a sensing resource? Can you build interaction graphs that allow you to realize toy models of quantum gravity? Can we start to study frustrated systems that map onto hard optimization problems? And can the quantum system help you solve those? And for the particular case of the number partitioning problem, if you want to read about ideas we've been thinking about, there's a recent theory paper in the archive here. So with that, I will just conclude by thanking my group. In particular, I think it's worth pointing out Avik Perewal was a undergraduate at Caltech with Nick Hutzler, and I'm very fortunate to have him as one of the folks doing these beautiful cavity QED experiments. And this is the Rydberg team. And with that, I will conclude and take questions.
Thank you very much, Monika. I'll help field the questions. If anyone has questions, you can type them into the Q&A and I will read them, or you can raise your hand and we can attempt to unmute you. We do have a question in the Q&A window, which I will read aloud. For your slide about programmable interactions, there seems to be a pattern to some of the noise on the correlation plot. Can you comment on the origin of these undesired correlations? And I think the question popped up when you showed the first sort of correlation chart from the programmable interactions.
Was it this one? This one? First correlation plot from the programmable interaction.
Yeah. Oh, that first correlation plot was me guessing based on the time, but maybe it was the second one. I guess
Ryan has his hand up. I'm gonna unmute him.
Oh, super. Thank you.
Oh, thanks. Yeah.
Hi. Yeah, that plot right there. In addition to the diagonals, there seem to be kind of less slopes, like diagonals with a more moderate slope.
Yes.
And it
Great.
seems like a pattern. I wondered if you can comment on that.
Yeah.
Thanks.
So this is actually showing correlations that are at some multiple of the distance where the interactions are on. And actually, the full sort of 2D correlation plots, I'll show at a later point here. This is an example of like correlation between, +1 atom on site I and -1 atom on site J. And you'll see that the interactions are at a distance of 2, but you actually have correlations at multiples of that distance. And similarly, this is probably actually the same data set. That's what's going on here. Now you could ask, why is that there? There are two reasons it might be there. One would be like maybe your drive is non-ideal and you have some higher harmonics in your drive field, or the other is that actually the correlations are in fact are in fact spreading, first going sort of 2 sites away, but then from there spreading to 4 sites away and 6 sites away. And we have pretty carefully checked that it's not just higher harmonics, and it really is that there's actually and it also kind of matches simulations that you expect the correlations to spread in this way. So that's the story there.
Great, thank you.
Yeah.
All right, thanks for the question. We have another one in the Q&A window. How do you generate a constant magnetic field gradient in the lattice?
To generate the magnetic field gradient, actually there are different ways you can do this. The data I showed are all taken just using, there's a large pair of anti-Helmholtz coils that generate the gradient. So that, that gives a uniform gradient. I'll mention that actually there's another way to generate the gradient, which is optically, by using some AC Stark shifts. You can make an effective magnetic field. And that's also something we explored that lets you make a gradient that requires some more control to make a uniform gradient, but then also gives you some extra knobs for controlling the interactions, because if you want, you can make it non-uniform. So hopefully I answered the question, but also just added one extra piece there.
Sorry, thank you for the question. Maybe I'll take my moderator's privilege to ask a general question, which is, can you comment on what are the bottlenecks to implementing these entanglement enhanced metrology tools in the sort of many different metrology applications, which generally don't use any sort of quantum enhancements? Like, meaning, is it more technical? Is it that there are sort of theoretical implementation problems?
I think it depends now a little bit on the applications. And so probably, I would say the nearest term is probably in clocks, where I guess there was recently a nice experiment actually showing entanglement on the clock transition in ytterbium. or squeezing on the clock transition in the terbium. And these tweezer clocks that Manuel works on, for example, are also like a great place where it seems really natural to engineer entanglement and then also have a really high level of kind of detection and characterization capability to understand it well enough to use it in a metrological way. I think this is definitely one of the bottlenecks, is kind of concern about systematics is one, right? That if you're really going to use it in sort of a real precision measurement, you definitely don't want to just add extra uncontrolled systematics. And then also just sort of, I think it's always easier to sort of build one setup that's just optimized for realizing these whatever interactions you want to use to generate entanglement without being optimized for kind of everything else, right? So I think partly it's just a matter of time to bring different technologies together, be that atom interferometers and cavities, or right, yeah. So.
And maybe I'll ask another more sort of practical question. If you could compare and contrast using Rydberg dressing versus just Rydberg excitation, as you mentioned a few of the advantages, such as the ability to sort of make more tunable and controllable interactions. But can you comment on, I guess mainly comparison to direct Rydberg excitation in terms of, say, strength of interaction, or state lifetimes, or other relevant parameters for these experiments?
Yeah, so overall the scaling is that you do lose, in terms of interaction to decay ratio, you do lose something by going further detuned at kind of fixed laser power, and often laser power is a limitation. That said, if you look at kind of numbers, something like 1,000 fundamentally like 1,000-to-1 interaction ratio at like a reasonable interaction to decay ratio at a reasonable laser power by dressing, like on paper looks achievable. I think what's been demonstrated is more like 100-to-1 now in kind of 1D chain systems. Now the challenges are there can be some dissipative effects that involve, for example, if you have one decay that can trigger additional decays. And that's something that at first, sort of in some early experiments, kind of looked like a showstopper. But that was, I would say, partly a matter of parameter regimes. In our experiments, that is not an effect that we see, but we realized another thing, which is that laser noise can actually matter more than one might naively expect for something where you're far detuned. And that's because even any sort of noise in the wings of the laser spectrum can affect you. And so we have kind of hypothesized that we did see some dissipative effects that we have hypothesized are related to laser noise. And one of the things that we're actually kind of now soon will explore is that in fact, is that true, and does it go away when you improve the laser spectrum and filter out that high frequency noise? Yeah, so I think in terms of like the fundamentals, if all you care about is maximizing the interaction to decay ratio, then sort of the biggest interaction you get is just having two atoms that are in the Rydberg state, and you divide that by the Rydberg state lifetime, and you don't win any penalty from being detuned. But it does restrict the forms of interactions that you have access to. And so to me, the dressing looks like, I would say, a useful complementary tool where the fundamental limits of coherence, I don't think have been reached yet. So.
All right. Yeah. Thank you. Thank you for explaining that. And the other question too. I'm excited about doing entanglement enhanced precision measurements, but yeah, I think I hope that people like you keep actually figuring out how to do it. People like me can maybe do it one day. So thank you very much for joining us. Let's all virtually thank Monika for a very interesting talk. And thanks to everybody for coming.
Thanks again for the invitation.